black holes, the cosmos, space and time travel, science and technology. Brought to you by theoretical physicist, futurist, popularizer of science, and world-renowned author, Professor Michio Kaku.
And GCNlive.com.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, we're going to throw the lines open. This hour is your hour. You own this hour. This hour is for you. This hour is for you to call the following number and ask a question or making a comment about any aspect of science. The number to call is 612-564-8135. Write that number down, 612-564-8135. That's the magic number. What I want you to do is when you hear the sound of the telephone, give your name, call letters of the radio station or website you're listening to, and the city you're calling from, and that's it. Then ask that question. Make that comment that you've always wanted to ask but never had the opportunity. You know, I was on a book tour a few years ago, and a guy comes up to me and says, "You have to answer my question." And I said, "Well, why do I have to answer your question? I will, of course, but why do I have to?" And then he said, "Because if you don't answer my question, I'll have to wait another 10, 20 years for another theoretical physicist to come and give a book tour." And I thought to myself, and I said, well, gee, that's right. He will have to wait about another 10 or 20 years for another theoretical physicist to come by to answer that question. So you don't have to wait 10, 20 years. You can call 612-564-8135. Let's say you're having dinner with the kids, and the kids ask you a science question from class that leaves you stumped. What are you going to do? Say to your kids, talk to your mother. No, you're going to say, I'm going to call Dr. Kaku and put you kids on the air. You can ask that question to 100 radio stations that carry Science Fantastic. And so once again, the number to call is 612-564-8135. And also, if you want to know more about what I do, go to my website, mkaku.org, mkaku.org. On Facebook, we passed 4 million fans on Facebook. On Twitter, we have about 1 million people on Twitter. And on my website, mkaku.org, you can see reference to the books I've written. I've written 4 New York Times bestsellers. My latest one is called The Future of Humanity, Humanity in Outer Space, as we head to the moon, Mars, and beyond. Another one was The Future of the Mind, talking about telepathy, telekinesis, mind reading, all the stuff that you read about in science fiction but never knew it was actually possible using advanced physics. By connecting the human brain to a computer chip, to a laptop, to the internet, you can literally control things around you by thinking about it. That's right, thinking about it. And then in Physics of the Future, I talk about artificial intelligence. I talk about the medicine, where medicine is going with genomics. I talk about how we will live in the future. And then in Physics of the Impossible, I go way out there, and I talk about Star Trek. I talk about science fiction, teleporters, warp drive, black holes, wormholes, hyperspace. All the stuff you see on Twilight Zone or on Star Wars, I talk about from a scientific point of view. So once again, go to my website, mkaku.org, and find out what all the excitement is about. Okay, well, without further ado, let's throw the lines open. And again, if you want to get on Science Fantastic, give us a call. 612-564-8135 is the number to call. Okay, let's take the first listener phone call.
Hello, Dr. Kaku. It's me, Harrison. am 6 years old from Moss Beach, San Luis Obispo, California. I was wondering, how is light made? Thank you.
Well, light is made, let's say, in a light bulb when you heat up metals like tungsten, for example. In fact, anything that's hot, if you heat it up to a few thousand degrees, it starts to luminesce. That's called black body radiation. Now, first of all, we have something called the conservation of energy, meaning that energy can change forms rapidly. The total amount of energy remains a constant. However, the form that energy takes can change. Specifically, if you heat up something to a few thousand degrees, it turns red hot. If you heat it up some more, it turns yellow hot. If you turn it up even more, it becomes blue hot. Now, why is that? Because the atoms inside the object you're heating up starts to vibrate. And it's the vibration of the atom that gives off light. Why does the sun shine? Well, the energy of the sun comes from E equals mc squared, Einstein's equations. But where does the light come from, the sun? It's because the atoms in the sun vibrate. And when they vibrate, they release radiation. If they vibrate very slowly, they release radio. In fact, that's where radio comes from. Radio comes from vibrating the atoms inside the antenna. If you heat it up some more, it turns into infrared hot. You heat up a wire some more, turns red hot, yellow hot, blue hot. If you could heat it up some more, it becomes invisible again, and becomes X-rays and gamma rays. And so once again, to answer your question, it is vibrating atoms. Atoms which vibrate, releasing radiation called black body radiation. That's why the sun shines, because the atoms inside the sun are vibrating. So why don't we shine? And the reason why we don't shine is because we're not hot enough. But if you were to take a piece of wood and heat it up to a few thousand degrees, it will in fact shine. Okay, well, let's move right on and take the next listener phone call. Hello, you're on the air.
Carla, 7:50 a.m., Anchorage, Alaska. The question is, if the universe is expanding, what is it expanding into? If it's expanding into other universes, what's the ultimate place or space, or what? All these universes are expanding? Where to? I know it sounds silly, but space, is it infinite? And is everything expanding infinitely? Or where's the edge? Thank you.
Well, you ask a very embarrassing question. It's sometimes said that physicists never blush when you ask them a question, but there's one question that will make a physicist blush, and that is, what is the universe expanding into, and where did it come from anyway? What happened before the Big Bang? That's how you can make a physicist blush. Well, there's two answers to this question. If I take a flat sheet of paper and then all of a sudden magically turn it into rubber, and then stretch the rubber can stretch. So every point on the rubber is stretching. But what is it stretching into? Well, it's just stretching in the second dimension, because you have a tabletop with a piece of rubber on it. Well, that's not very satisfactory for most people. But we physicists now have a new idea coming from hyperspace. So let's take a short commercial break, and after the break we're going to continue a discussion of what is the universe expanding into anyway. You are listening to Science Fantastic. The number to call is 612-564-8135, and ask that question that's always been bothering you for all these years. So stay tuned now for Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. This hour is your hour, so once again, get to the phones and call that number, 612-564-8135. Leave your name, call letter to the radio station or website, and the city you're calling from, and bingo, maybe you can get on national radio. Well, before the break, we had a very embarrassing call from someone who asked a question that even children ask. When children learn that the universe is expanding, the first thing they say is, well, if you're so smart, tell me what is it expanding into? Well, the short answer is we don't know. But there are theories. The latest theory comes from something called string theory, which is what I do for a living. That's what I get paid to do by New York State, working on string theory. And that is that our universe is a bubble of some sort. It's expanding. We live on the skin of the bubble, and that's called the Big Bang Theory. The fact that we're probably on a bubble of some sort that's expanding. But we now believe that there are other bubbles out there in a multiverse of universes, each one perhaps expanding or contracting. And what is it expanding into? Well, the bubble is three-dimensional. It is our universe. We can move left, right, up, down, forward, backward. We can move in three directions. However, if we're on a bubble, the bubble is expanding into another dimension, a dimension that we cannot sense because we're trapped. We're trapped on the skin of a bubble. So we can do the mathematics of what it would take to leave the bubble and float in hyperspace, that is a higher dimension, but we can't do it because we are stuck on our bubble. Sorry about that. So to answer your question, the short answer is that our bubble is expanding. It's expanding into the 11th dimension. So we live in a three-dimensional world. With time, it's four-dimensional. But there are other dimensions that we cannot see. So we're like ants. Ants stuck on a bubble, like a balloon. The ants can theorize about the third and higher dimensions, but they can't escape the bubble. They're stuck like flies on flypaper, and that's why they cannot visualize these higher dimensions. And again, this is just a theory, but it happens to be the dominant theory in theoretical physics at the present time. Okay, well, let's move right on to the next listener phone call.
Hi, my name's Maria. I'm calling from Queensland in Australia. I'm listening online, and I was wondering how black holes close, but also if you could explain what happens to the antimatter when it reacts inside the black hole. Does it turn into a photon, or what type of energy does it turn into when it annihilates? If you could please explain this. Thank you.
Wow, we get so many phone calls talking about the cutting edge of physics. So let me try to answer your question. First of all, what is a black hole? A black hole is like a dead star or a collection of dead stars that is so massive that even light cannot escape. So it's not that the black hole closes. The black hole is like a Roach Motel. Everything checks in, nothing checks out. And surrounding the black hole, there's a sphere. The sphere is called the event horizon. If you pass through the sphere, you never come back out again. It's a one-way trip. If you skim the surface of the sphere, you orbit around the black hole and do not necessarily die. You can simply orbit around the black hole. That's what we do, by the way. We are orbiting right now around the black hole. There's a black hole in the center of the Milky Way galaxy in the direction of Sagittarius. If you want to see it tonight, look in the night sky, look in the direction of the constellation Sagittarius, and there's a black hole that weighs about 4 million times the mass of our sun. And so the black hole doesn't close. It's basically a trap door where everything can fall in and nothing falls out. And we have photographed it. It was a photograph that made headlines around the world. It looks like an angry eye. You see this black thing in the center, which is the event horizon. It is black because everything that falls in is captured and nothing falls out. And then what about matter, antimatter? Well, Stephen Hawking said that black holes are actually gray. They can seep out a little bit of radiation called Hawking radiation. So let's say that the gravitational field of a black hole is very strong, so strong that matter and antimatter spontaneously jumps out of the vacuum. It's possible one particle falls into the black hole, the twin, the counterpart, leaves the black hole, so the black hole radiates. It gets smaller and smaller less massive as time goes by, it will radiate, called Hawking radiation. It's very slight. Now, the reason why I think Stephen Hawking never won the Nobel Prize for this idea is because it's experimentally very difficult to test. How do you test this very faint radiation that comes from a black hole when matter, antimatter pops out of the vacuum? One particle falls into the black hole through the event horizon. The other particle escapes as Hawking radiation. So it's a theory. Everyone believes in it because it obeys quantum theory, so we all believe that this happens. But to prove it is difficult, and so far we have not observed it. And that's why I think that the late Stephen Hawking never really won the Nobel Prize for a stunning application of the quantum theory for black holes. And then the next question is, let's say you fall into the black hole, where do you go? The short answer is we don't know. There are many theories. Most theories simply say you get crushed and that's the end of the story. Another theory says that perhaps there's a gateway to the other side of a black hole. We don't know. If you just take a look at the theory, just take a look at Einstein's equation, throw something into a black hole, what happens to it? It falls into a parallel universe, especially if the black hole is rotating like a very fast ring. However, is there proof of this? No, it's just theoretical. But the existence of black holes is no longer in doubt. We see them, we can photograph them, and there's one right in our own backyard in the direction of Sagittarius. Okay, let's move on to the next listener phone call.
Hello, Dr. Kaku. My name's Jason Miller from Fredonia, Kentucky. I listen to your podcast online. My question is about the origin of time. Do we know how long it took from time to go from infinity to the current rate that it goes now on Earth? And how do scientists calculate those things? Or can we even look back that far? Love to hear your thoughts. Thank you.
Well, that was the question facing Edwin Hubble, the famous astronomer, back in the 1920s. When he took a telescope and looked at the far distant galaxies, he found that the light, which should have been yellowish, was actually slightly reddish. Now, what does that mean? This is called the Doppler Effect, the fact that when something that vibrates moves away from you, the wavelength stretches like an accordion. If an object that vibrates moves toward you, then the waves are compressed like an accordion. Now, sound waves have this feature called the Doppler effect, and let me demonstrate for you what it sounds like. When a car comes toward you, it sounds like this. That's when it moves away from you. The frequency drops. So the frequency is higher when it moves toward you because light is compressed or sound is compressed, and sound drops in frequency when it moves away from you because sound is stretched. Now, you've heard that all your life. All your life, you've heard the sound of cars whizzing by, except you never knew there was a name for it, called the Doppler Shift. That, however, the reason why policemen give you speeding tickets. They shine a laser beam on your car, and the laser bounces off your car and is slightly distorted. And if the frequency is raised, it means that you are moving away from the cop car, or moving toward the cop car. If the frequency is lower, it means you're moving away from the cop car. So that's how cop cars know how fast you are traveling. Now, Edwin Hubble in the 1920s found that the galaxies in the heavens were slightly reddish, meaning that they were moving away from us. And he found something called Hubble's law. The farther you are away, the faster you're moving away from the center. Well, I'll talk about the origin of the universe after the break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. Give us a call. Ask that question. 612-564-8135 is the number to call, and you can get on Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. You can ask a question on national radio. The number to call is 612-564-8135. Well, we had a question coming in, and the question was, how do we measure time? How do we know how old the universe is? For example, no one was there. No one was there to witness the Big Bang, and our clocks only go for a few hours today, so how do we measure cosmological time? And the way we do that is by looking at the redshift. That is, galaxies are moving away from us, and we know the rate. We know the rate at which they are moving away from us, and we know how far they are away. So what you do is you calculate how fast a galaxy is moving toward you, and then just run the videotape backwards. When you run the videotape backwards, you get a time of when the galaxy was right close to you, like in a Big Bang. So that's how we calculate the age of the universe, by calculating how fast the galaxies are moving away from us, and then running the videotape backwards. Now, originally, when Hubble did this calculation years ago, he came out with an embarrassing conclusion. He found that the universe was something like 1 billion years old. But you see, geologists already knew that the Earth was billions of years old, because that's what it takes to create mountains and continents and continental drift. Well, we have a better measurement now with satellites. With satellites, like the Planck satellite, the latest number, ta-da, is the universe is 13.8 billion years old. So again, by running the videotape backwards, that's how we can calculate how long it took for the expanding universe to get as big as it is. And the answer is 13.8 billion years, which matches all the other yardsticks that we have. We know the age of stars, for example, so the universe has to be older than the stars, of course. And sure enough, 13.8 billion years is older than the oldest stars. And so that number seems to hold. And so we now know more or less how old the universe is. Now, Stephen Hawking took this one step farther. I wouldn't go this far. Stephen Hawking said that because we know the instant of creation, the Big Bang, there was no time for God to create the universe. Therefore, God doesn't exist. Because the universe took place in an explosion, and there was simply no time for God to create all the planets and stars and trees and birds and stuff like that. Well, now we believe in a multiverse idea. It's not proven, but it's the leading theory now that we live in a bubble bath of parallel universes. And so there is a time before time. There was a time before the Big Bang. And therefore, if God exists, there's plenty of time for God to create a multiverse of universes. Okay, let's move on now to take the next listener phone call.
Yes, Professor, this is Roy Martinez calling on 89.9 KWCB in Floresville, Texas. I have a question about Halley's Comet. It goes through the Earth's atmosphere every 78, 79 years. Okay, my question is, if somehow we could put a GPS and trace it, where does it go? Does it go all the way to the end of the universe and it goes around and comes back around again? That's what I'm curious about that. And thank you for your time.
Okay, well, let's take another short commercial break, and after the break, we're going to answer the question, where do comets come from anyway, like Halley's Comet? Well, you're listening to Science Fantastic. Give us a call at 612-564-8135, and you can get on Science Fantastic. Give us a call. Welcome back to Science Fantastic with Professor Michio Kaku, and if you want to know more about Science Fantastic, and what I do, go to my website, mkaku.org, mkaku.org, to find out what I do for a living, which is physics and science. Well, before the break, we had a call about where did Halley's Comet come from, and where do comets come from in general? Well, when we learned about our solar system, we learned that the planets toward the center of the solar system are the rocky planets, Mercury, Venus, Earth, Mars. Further out, you have the gas giants like Jupiter, Saturn, Uranus, Neptune. But what's beyond the gas giants? Beyond the gas giants, there are comets. And there are two types of comets. Some comets are in the disk of the solar system. They're called short period comets. They can whiz around the solar system in a matter of years to decades to centuries. These are comets that lie slightly outside Neptune, but not much farther than that, in the disk of our solar system. But then we have a sphere of comets called the Oort cloud, and that's where long period comes from. Long period comets come from. Now, Halley's Comet is a short period comet. Its orbit takes it out to around Neptune or so, and as you pointed out, every 76 years it whips around the solar system, giving a spectacular cosmic display. Now, then the next question is, well, if it comes back every 76 years, that means that maybe the cavemen and cavewomen saw the comet. Well, yeah, perhaps they did, but recorded history with the Chinese and people in the Middle East, we've been able to go back thousands of years into the past, and sure enough, every 76 years or so, Halley's Comet reappears in the sky. We should also point out the historic importance of that comet. That comet sailed over England in the year 1066, freaking out King Harold's troops, which were in a life and death struggle with William of Normandy. Well, William of Normandy won the Battle of Hastings, creating the modern British monarchy. So in some sense, Halley's Comet was sort of like a midwife to the creation of England. That's right. And then that same comet, the same comet that helped to create England, also sailed over London again around 1666 or so. A young gentleman saw that comet by the name of Isaac Newton. His university was closed because of the Black Plague. England was in a lockdown because of the Black Plague. And while he was at home looking at comets, he discovered the law of gravity and the laws of mechanics and motion, one of the greatest achievements of the human mind. So Halley's Comet, in some sense, was the midwife of the British monarchy and the midwife of Newtonian mechanics, which made possible the Industrial Revolution. Not bad for one comet. Okay, let's move on now to take the next listener phone call.
Hi, Dr. Kaku. My name is Kenneth. I would like to ask if we were living on another planet and there was, like, for example, a ring, you would see ring shine. But let's say you were living near a nebula, would you see, like, nebula shine? Or if there was a black hole, a very large black hole that was far away but still large in apparent size in the planet's sky, would that be called, like, singularity shine, if you would sort of see, like, some kind of, like, a light emitting from the black hole towards the planet that you're on? So wouldn't that be called, like, event horizon shine or singularity shine? One last thing, let's say there are multiple universes and you're in a multiverse and you're looking out from your universe to another universe, you see it rise above you. Would that be like Cosmo Rise or, like, you know, something like that? Thank you.
Well, to answer your question, many people saw the movie Star Wars, where Luke Skywalker looks up in the sky and sees a double star system. Well, a lot of scientists wrote letters saying that's nonsense. It's unstable. Planets cannot go around a double star. You're not going to have double star shine in the universe. Well, they were wrong. Now we have 4,000 planets that we've seen orbiting other stars, and sure enough, some of these planets orbit not just double stars, but triple star systems and even more. So yes, you can have double star shine, the shine from two stars. However, black hole shine is going to be much more difficult. So sorry about that. Black holes are black. They absorb light. They don't give off light at all. So you're not going to see black holes shine. Sorry about that. Well, let's take another short commercial break. You're listening to Science Fantastic. Give us a call at 612-564-8135, and maybe you can get on national radio. So give us a call and ask that question that you've always wanted to ask on national radio. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. You can always give us a call by calling 612-564-8135. Leave your name, call letters at the radio station or website, and the city you're calling from, and maybe you can get on Science Fantastic. However, let me finish up the response I made to the person who talked about moonshine, starshine, and black hole shine in outer space. Why can't we see the black hole at the center of the Milky Way galaxy? Well, one, it's black, but it's at the center of the galactic cluster. In other words, by rights, there should be a fireball, a gigantic fireball bigger than the moon, coming out every night. Think about it. A gigantic fireball that outshines the moon every night, which is the galactic center. At the center of the galactic center in Sagittarius A, there's a black hole. Now, by rights, so there should be a fireball coming out every night, which creates not just moonshine, but galactic nuclei shine, which would then light up the night sky. Why don't we see it? Dust clouds. We live in the disk of the Milky Way galaxy. The Milky Way galaxy is like a disk, like a flying saucer. And because we are in the disk, and the disk is quite dusty, we cannot see the galactic center. But if you could somehow by magic remove all the dust in the galaxy, then you would see this fireball coming out at night, and yeah, you would see definitely galactic nuclei shine, outshining the moon with a black hole at the very center. But sorry about that, it's all obscured by dust clouds. Okay, well, let's move on and take the next listener phone call.
Hello, Dr. Kaku. This is Ben Parno calling from Waukesha, Wisconsin, and listening to you on YouTube. My question is, if you had the opportunity, would you drink a glass of Europa water? And with that, is there a possibility that it could be some kind of different kind of water? Or is water water no matter where you are? Love your show. Thank you for being amazing and teaching me so much. Bye.
Well, to answer your question, water is not always water. There's something called heavy water. You see, water is H2O. That is, you have one oxygen atom with two hydrogen atoms. But hydrogen occurs in more than one variety. You can have ordinary hydrogen with one proton, but also you have the deuteron, so you have a proton and a neutron. So it doubles the weight of hydrogen without changing the chemical properties. So instead of H2O, you have D2O. Now, D2O, if you were to drink it, from what we can tell, is harmless. It tastes just like ordinary water, except a little heavier. That's why it's called heavy water. And it would have no health effects. So when we analyze ancient water, water from the glaciers, water that's been frozen in the glacier ice for tens of thousands of years, we find that the ratio between ordinary water and D2O is slightly different. And that's how we use as a dating material in order to calculate the age of these glaciers. So how do we know what the weather was like so many tens of thousands of years ago? Because the ratio between water and heavy water actually changed over the thousands of years. Now, you also asked another question, would I drink Europa water? Well, probably not. First of all, Europa is a satellite of Jupiter. It has an ice-covered surface, and geysers apparently shoot sprays of water and ice into outer space, but it probably has lots of contaminants as well. I mean, Jupiter, of course, is a gigantic radioactive planet, and so the water on Europa is probably slightly radioactive, plus contaminated by all sorts of chemicals. So I would not definitely drink Europa water. However, NASA had at one point plans to put a submarine in under the ice cover of Europa. So once again, this is a moon of Jupiter. It is, of course, a billion miles in outer space. It's covered with ice, but underneath it is an ocean of liquid water, and plans to put a submarine down there are plausible, but has been shelved at the present time. But it means that life may actually exist in the far reaches of the solar system, far away from the sun, where tidal forces, that is, a churning of the center of Europa, keeps it hot, melting the ice cover, creating a liquid water ocean. But to answer your question, would I drink the water? No. It's probably radioactive and full of contaminants. But D2O and H2O apparently are cousins. They are chemically identical. Okay, well, let's move on to the next listener phone call.
Hello, Michio Kaku. My name is Orlando, and I'm calling from Stuart, Florida. My question is, what is the best theory on what happens after death? And are you afraid of death? You're my hero and icon, and I've enjoyed listening to you very much. Thank you very much.
Well, first of all, let me say very clearly, I don't know what happens after death. If you talk to most scientists, they would simply say that death is a cessation of biological activity, so your body, as we know it, can no longer function. But what happens to your soul after that? Well, we don't know. However, let me say a few things. First of all, it's normal to fear death because we are hardwired to do so. We are hardwired to protect ourselves. If you don't believe that, simply throw something at somebody and instinctively they'll try to catch it or dodge it. You have no choice. So we are genetically hardwired to fear death. But what happens after death? Well, I wish I knew. I could change world history if I knew the answer to that question. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we look at the headlines. We look at the recent developments in science, things that are going to shape the way we view the universe and perhaps even change our lives. And once again, if you want to get on Science Fantastic, give us a call. The hotline number is 612-564-8135. Once again, if you want to get on Science Fantastic with Professor Michio Kaku, the number to call is 612-564-8135. And go to my website to find out what I'm up to. My website is mkaku.org, mkaku.org. I'm a professor of theoretical physics at the City College and the City University of New York. I've written 4 New York Times bestsellers. My latest bestseller is called The Future of Humanity, Humanity in Outer Space. What happens if one day we begin the colonization of Mars and even the solar system and beyond? And I'm on a book tour. Go to my website, mkaku.org, mkaku.org, and maybe, just maybe, I'll be in a city next to you signing your copy of my latest bestseller. And after I sign your book, well, you can go to eBay and auction them off for money. That's right, signed books are worth money, and you can actually make money by going to my book tour. Well, once again, the lines are open. If you want to get on Science Fantastic, there's no mystery. Just call 612-564-8135. All we ask is that you leave your name, call letter to the radio station you're listening to, if you're listening to one, and the city you're calling from, and ask that question. Make that comment that you've always wanted to make, but you just never had opportunity. And some of you may say to yourself, oh, come on. I mean, I can't get on national radio. My question is too dumb, too stupid. People will laugh at me. Well, it turns out that, first of all, chances are if you have a question, I think perhaps hundreds, thousands of other people will have that identical same question. And just realize that sometimes some of the dumbest questions are the most profound of all. For example, years ago, there was a 16-year-old boy who asked himself a dumb children's question, and that is, can you outrace a light beam? Such a dumb question. Well, it took him 10 years to finally find the answer. When he was 26 years old, he finally found the answer. The answer was in a theory called relativity. His name was Albert Einstein. And so one of the greatest theories of all time simply came out of a question that any child would ask, such as, can you outrace a light beam? And the answer, by the way, is no, you cannot outrace a light beam. And because of that, you have to have enormous distortions of space and time preventing you from outracing a light beam, and that is called relativity. And one of the simplest consequences of relativity is the atomic bomb. So, once again, if you want to get on Science Fantastic, the number to call is 612-564-8135. Okay, well, let's move right on and take the first listener phone call.
Hello, Dr. Kaku. This is Kenneth from Hollywood, California. I read about an object called the black brain, which is a singularity in the form of a membrane. Is there such thing as a white brain, that is, the white hole in the form of a membrane, be it 3- or 4-dimensional? I already know that white holes and black holes are, but since scientists speculate something called the black brain, perhaps there's a white brain, a big bang in the form of like a 3-dimensional bulk.
Okay, well, you ask a question that's at the forefront of theoretical physics. So let's back up several giant steps and take it one at a time. First of all, what is a brain? A brain is not what's sitting on your shoulders. To a physicist, it is B-R-A-N-E, as in membrane. Now, we physicists believe that strings are the fundamental building blocks of the universe, but strings also coexist with membranes, like a beach ball, like a sphere, like a baseball. They are membranes, and they also vibrate, and they can also create particles. And now, this theory is not verified. However, many physicists work on this. I work on it, in fact, and we think that that is what the universe is made of. The universe is made out of strings and brains. In fact, our universe is a membrane of some sort. And then the question is, there are black brains, just like there are black holes. There are solutions of the string equations, which give you black holes. In other words, string theory includes all of Einstein's theory of gravity. Einstein's theory of gravity says that if you compress mass dense enough, it'll collapse into a black hole. Well, now we have strings, and sure enough, if you collapse strings into a tiny, tiny point, then the strings will collapse into a black brain. And believe it or not, we hope to actually create them with the Large Hadron Collider outside Geneva, Switzerland. That's right. Believe it or not, we hope to actually create black holes and black brains in Switzerland. Now, don't get scared. We're not talking about mammoth black brains and black holes that can gobble up entire stars. No, these are subatomic particles. Your body is bombarded with subatomic particles by the millions every day, and you don't even feel it. So we are talking about subatomic black holes or black brains, which are the collapsing of these brains into a very, very tiny mass. Now, the question you ask is white holes. So let me explain. Matter falls into a black hole. But according to physics, you can also reverse time, have the time run backwards, and that is also a solution of Einstein's equations. That is called the white hole. Instead of matter falling in, like in the movies, all these Hollywood movies show starships being eaten up by a black hole, this shows that you can have a time-reversed object called the white hole, where matter comes out, not in. And some people think, aha, maybe that's the Big Bang. In fact, there is a theory proposed by several physicists that maybe the Big Bang is really a white hole, such that matter spews out rather than in. Now, let's be fair about this. We've looked for white holes in the universe. We have seen none. That doesn't mean they don't exist. It just means that they're rather exotic. And so black holes, yes, we've seen them in outer space. In fact, with the Webb Space Telescope to be launched very soon into outer space, the replacement for the Hubble Space Telescope, we hope to even get better pictures of these objects, the swirling disk around the black hole. And so then the question is, are there white holes? We don't know. And white brains may exist, but they're even more exotic than white holes. So the answer to your question is, we don't know. We do think that black brains exist. However, we have no proof. String theory itself has no proof, but it is the leading theory to replace Einstein's theory of relativity. And if you want to find out more about it, because this is actually what I do for a living, this is what I do for my day job, get a copy of my earlier books, Parallel Worlds, where I talk about M theory, string theory, brains, and the zoo of objects which we think may ultimately create our universe. Okay, well, unfortunately, we have run out of time in this segment of Science Fantastic, but stay tuned. Welcome back to Science Fantastic with Professor Michio Kaku, and the lines are open. This is your opportunity to get on national radio and ask that question, make that comment that's always been bothering you, but you just never had the opportunity. Maybe you're walking down the street and you look up, you see maybe the moon. You see the mountains, the wind. At night, you see the stars. And then you ask a question, what does it all mean? I mean, where did it all come from? Where is it going? Or you look at the economy and you realize, oh my God, artificial intelligence, computers, all that is changing so rapidly. What will the future look like? Well, first you can go to my website and check out my books where I talk about the future of society, the future of medicine, the future of artificial intelligence, jobs, who will have a job in the future. These are things I address in my book, The Future of the Mind, and also the physics of the future. Go to my website, mkaku.org, mkaku.org, and you can see the books, 4 New York Times bestsellers, where I talk about your future. And so once again, if you want to get on Science Fantastic, give us a call and leave that question. Make that comment. The number to call is 612-564-8135. And I'm on a book tour. Find out what cities I'll be traveling in, and maybe I'll be coming by a city next to you signing your copy of my bestsellers. Okay, let's move on now to the next listener phone call.
Hi there, Dr. Kaku. This is Lance Rome. I'm calling from Green Bay, Wisconsin, and I listen to you off of your website. I have just a few quick questions about the Big Bang. Is the edge of the visible universe the current extent of the Big Bang? Is the expanding force producing light? Is the expanding force producing heat? And if so, is the heat similar to when it first banged? Thank you for your time.
Well, you ask a lot of questions that are very difficult to answer because we're not really sure about these things. But let me tell you what is known about some of your questions. First of all, the Hubble Space Telescope can peer into the past. The night sky is a time machine. So the moon is 1 second away from us. Light takes 1 second to reach the moon. The nearest star is 4 light years away from us. It takes 4 years for a flashlight from the Earth to reach the nearby stars. Andromeda is the nearest galaxy to the Earth, and that is several million light years from Earth. But the Hubble Space Telescope can see even farther. And when he goes farther and farther, we're talking about going back billions of years into the future. The Hubble Space Telescope can actually photograph objects almost 13 billion years ago, because we think the age of the universe, in fact, is 13.8 billion years. That is the age of the universe. Now, you ask a question, and the question is, what is at the edge of the universe? Well, the edge of what the Hubble Space Telescope can see is the Big Bang itself. That is, this Hubble Space Telescope, when it looks at the farthest star, goes beyond the farthest star and sees blackness. There's only blackness there beyond the farthest star. But that blackness is deceptive. It's actually microwave radiation. It's actually the radiation of the Big Bang itself. So if your eyes could see microwave radiation, then every night you would actually see the remnants of the Big Bang. Believe it or not, if your eyes could see microwaves, you would see this haze, this explosion, the remnants of the original Big Bang. Now, the question was, is this the edge of the universe? And the answer is no. This is the beginning of the universe, not the physical edge of the universe, okay? So the Hubble Space Telescope sees starlight that is very old, older than the dinosaurs, hits our sensors in outer space and gives us a picture not of the physical edge of the universe, but the temporal edge of the universe. That is when time began 13.8 billion years ago. And then the next question is about the heat of the Big Bang. Where did it come from? Well, it came from something we call dark energy. We don't know what dark energy is, but it is the energy of the Big Bang. What is pushing the galaxies apart? Why is the universe expanding? We're not sure, but if you look at Einstein's equations and you put in what is called the cosmological constant or dark energy, the universe will expand, just like it seems to be doing right now. So it is the energy of the vacuum, the energy of nothing. This is hard to get your head around, but an empty space itself has energy, repulsive energy that is pushing the galaxies apart, called dark energy. Now, this means that the energy of the Big Bang is the energy of nothing, the energy of empty space. As the universe gets bigger, there's more empty space, and therefore there's more energy to push the universe apart. And therefore you go into a vicious cycle. The universe has a lot of vacuum. The vacuum has energy. Energy pushes the galaxies apart to create more vacuum, which creates more energy. Now, you may say to yourself, well, this all sounds bizarre, but hey, that's what the data is telling us. The data is telling us that the universe is accelerating, not slowing down. The data is telling us that perhaps it is the energy of the vacuum, the energy of empty space, that is pushing the galaxies apart. And again, if you want to know more about this, get a copy of my book, Parallel Worlds, where I give you the latest in cosmology. Okay, well, let's move on now to the next listener phone call.
My name is Dylan. I'm calling from Kennewick, Washington, listening on KONA 610. My question was what your opinion on Dr. Botwinsky from Texas and his anti-neoplasm therapy for cancer. Thank you. Bye.
Well, I'm not familiar with that particular person. However, I would be a little bit skeptical because it's very easy for people to make claims about cancer cures, but the excitement in cancer research is at the genetic level. Cancer is, in some sense, no longer a mystery. We can't cure all cancers, of course, but we know what cancer is. We didn't know that before, because we knew before that chemicals can cause cancer, viruses can cause cancer, sunlight can cause cancer. So if all these things can cause cancer, how are we ever going to get a theory, a unified theory of cancer? Well, what links chemical exposure, light exposure, X-rays, radiation, all that damage, what links them all together? And the answer is all of them create mutations. They damage our genes. And if there are approximately four major mutations in our genes, then you can basically dismantle the mechanism that prevents cancers from stopping, and they simply keep on reproducing forever until it kills you. So we know, therefore, that cancer is a genetic disease. And now we're attacking it at the genetic level. And so that's where all the excitement is. The excitement is, for example, immunotherapy, where you take white blood cells and immune cells from the body, grow them, strengthen them outside the body, and then re-inject them back into the human body. So we're basically enhancing a natural mechanism of the human body itself. And then we have yet another breakthrough being made in terms of cancer detection. Right now, you can have cancer. That's right. In fact, some of you listening to my voice probably have cancer growing in your body, but you don't know it. You won't know it, in fact, for many years. Maybe 10 years from now, you'll have enough cancerous cells to create a tumor, which may eventually kill you. So why can't we detect cancer now? not 10 years from now, but now, rather than waiting for a tumor to form. Well, this is where liquid biopsies come in, and DNA chips. We now have the technology to analyze DNA, proteins, cancer cells in blood, bodily fluids, years before a tumor forms. These are called liquid biopsies, and they're going to become commercially available very soon, and it could change the way we view cancer, and the word tumor could disappear from the English language. You're not going to get a busy signal. Give us a call. The hotline number is 612-564-8135. And check out my website. Find out what I'm up to. My website is mkaku.org, mkaku.org. It has many of my TV appearances, and also it has references to my 4 New York Times bestsellers. The latest one is called The Future of Humanity, talking about humanity when we explore outer space. But in The Future of the Mind, we talk about how we physicists are now unraveling the secrets of the living brain, telepathy, telekinesis, recording dreams, things that were once considered impossible, we do in the laboratory. And Physics of the Future talks about jobs. It talks about artificial intelligence, talks about medicine. What will the future bring us? Find out in my book, The Physics of the Future. And what about science fiction? Get a copy of my book, Physics of the Impossible, where I talk about Star Trek. I talk about Star Wars, or any of the gadgets, gizmos, and concepts found in science fiction based in reality. Find out by getting a copy of my book, The Physics of the Impossible. Okay, once again, the lines are open. You can give us a call at 612-564-8135. Let's move on now and take the next listener phone call.
My name is Casey on KFBX Fairbanks, Alaska. And my question is, can you make a coil out of fiber optic cabling, running light through the fiber optic cabling as a current would over copper wire in a coil, and somehow contain that with a magnetic field under a vacuum? Thank you.
Well, you asked 2 questions put together, so let's try to explain it. First of all, electricity, we know, would run in a wire, and we could extend wire hundreds and hundreds of miles, and yet electricity won't escape. It's basically sealed in that wire. Now with light, you can do the same thing with fiber optics, and we do that in glass. So if I have a glass cable, very thin, almost hair-like glass fiber, and I shoot a laser beam inside it, then the question is, can it escape? Well, the answer is no. You have something called total internal reflection. The light basically bounces off the inside of the fiber, and it never leaves the fiber, and that's called fiber optics. And that's where a lot of the Internet is now being conducted. The Internet, a lot of it is done with laser beams connecting cities, and it turns out that fiber optics is the backbone of the fiber optic cable. Then you ask yet another question, and that question is what the relationship is with magnetism. We know that if I have electricity and I shoot electricity in a wire in a coil, it creates a magnetic field. In fact, that's how you create magnetic fields, because electric fields, when they move, can create magnetic fields. Magnetic fields, when they move, can create electric fields. And that is the basis of the electric revolution. Welcome back to Science Fantastic with Professor Michio Kaku. And the lines are open. Give us a call. The hotline number is 612-564-8135. And all we ask is that you leave your name, call letters to the radio station you're listening to, if you're listening to one, and the city you're calling from, And hey, maybe your thoughts will be heard on almost 100 radio stations that carry science fantastic. And while you're at it, go to my website, mkaku.org, mkaku.org. On Twitter, which is called Michio Kaku, on Twitter, we have about 1 million people that dial into Twitter every week, according to the latest stats, and 3 million people that are on Facebook. So find out what all the excitement is about by going to my website, mkaku.org, mkaku.org. Well, before the break, we had a question about coils of light. We know that coils of electricity can create magnetism. In fact, that's how we create electromagnetic fields, by putting electricity in a wire, putting the wire in a coil, and bingo, magnetism occurs as a consequence of that. The question is, can you do that with light? And the answer is no. Sorry about that. Light is trapped inside the fiber optic cable. Now, light itself is a combination of electric and magnetic fields constantly changing into each other, creating a wave-like pattern. So we know what light is. Light, in some sense, is no longer a mystery. Light is the propagation of electric and magnetic fields constantly turning into each other, sort of like a snake that bites its own tail. So light is an electromagnetic wave. You can then confine it inside a tube of light, which is called a fiber optic cable. But does that create a magnetic field? And the answer is no. The magnetic field is inside the cable, not outside. In fact, outside the fiber optic cable, you basically see nothing at all. Okay, anyway, let's move on now to the next listener phone call.
Matthew Wilson, 1620 AM. I was wondering what your thoughts were on the artificial creation of plant life, botany, and artificially creating photosynthesis. And then I also wanted to ask your question on creating a invasive plant species artificially, and then using that with tailored genetic tampering to terraform planets such as Mars.
Well, you actually ask a question that I address in my latest book, The Future of Humanity, Humanity in Outer Space, where I talk about terraforming Mars. Now, Mars is a frozen desert, very cold. However, the atmosphere is made out of carbon dioxide, and plants love carbon dioxide, even though it's very cold and the atmosphere is very thin. And so some botanists have speculated that maybe what we have to do is genetically modify algae, genetically modify simple plants to thrive in the Martian atmosphere. And bingo, we've done that. It turns out that in the laboratory, you can breed and genetically modify certain plants so that they would thrive in a Martian-like atmosphere. Now, it's not going to be easy because, of course, Mars is frozen solid. But if you have like a mini greenhouse on Mars, you could then start to create life forms with minimal intervention. You just have to make sure the temperature is above freezing, and you can actually grow plants that will thrive in the Martian atmosphere. So this means that terraforming would proceed in certain steps. First of all, if you could raise the temperature of Mars by 6 degrees, just 6 degrees, then you would get a runaway greenhouse effect, and you would then raise the temperature of Mars even more automatically, all by itself. You see, water vapor is a greenhouse gas. If you could raise the temperature of Mars by 6 degrees, water vapor will form from the ice. The more water vapor you have, the more greenhouse effect you have, which will create more water vapor, and then you have a runaway greenhouse effect. Once that takes place, then you can unleash these algae on the lakes and the ponds and the rivers that are going to be flowing and being created on Mars. And so it'll have to take place in steps. But the key step, as you mentioned, is once we get this runaway greenhouse effect started, then we can start to take advantage of it to create agriculture on Mars. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. This hour is your hour. This is the time when you can get to the phones and give us a call. 612-564-8135. How many times have you been listening to the radio, read the newspaper, saw TV about some kind of breakthrough in science, about space, about medicine, about anything concerning our world, and yet you're all alone and there's nobody to talk to, and that's it? Well, you can talk to me. You can give me a call 24/7. You can call 612-564-8135. You'll get a recording. The recording will ask you for your name, call letters of the radio station, and the city you're calling from, and then ask that question that you've always wanted to ask but never had the opportunity. Well, here's your chance. Once again, the number to call is 612-564-8135. Okay, let's move on now to the next listener phone call.
Hi, Dr. Kaku. My name is Drew Jones. I'm listening on YouTube, and I'm calling from Anchorage, Alaska. Hey, I just had a question for you in regards to the Vostok ice core experiments that took place years ago. The way I understand it is that there were increases in carbon dioxide, and they were always accompanied by increases in temperature, but the increases in temperature always came first. And on another note, the increases in carbon dioxide consistently lagged behind temperature increases by about 800 years. So doesn't this prove that increased levels of carbon dioxide did not cause the warming if it didn't happen until after the warming? Thank you. Appreciate it.
Okay, well, you ask a very interesting question. First of all, I once had a chance to go to Iceland where I gave a lecture, and I visited the laboratory where they actually analyze ice cores. In Greenland, yes, you just go right outside, drill into the ice with a tube, take out the tube that you get, this cylinder of ice, and then you look at it, and it's quite amazing. When you look at this long tube of ice, you see horizontal stripes. Horizontal stripes in the ice representing volcanic ash. That allows you to date when this snow fell, because we know the dates of these volcanic eruptions very accurately. And so it's sort of like a fingerprint by which you can match these horizontal lines with the known volcanic eruptions to give a date. And how far back can you go? 600,000 years. This is amazing. Now, not only can you see the ash from ancient volcanic eruptions, you can also look at the air bubbles. By looking at the air bubbles and by looking at the composition of the air bubbles, you can actually calculate indirectly the temperature and the atmospheric composition during that time. This, again, is amazing. And then you plot it on a graph. You plot carbon dioxide on a graph, and you plot temperature on a graph, and you find something that's remarkable. You find two lines that are coincident, that go up and down at the same time. And so this means that there's a strong link between temperature and carbon dioxide. They go up and down like two roller coasters. Think of two roller coasters in sync, going up and down, up and down. Now, then the question is, which came first, the chicken or the egg? It turns out that many of these studies are not accurate enough to begin to distinguish exactly which led the other. There is a theory that you mentioned that maybe it was the temperature first, another that says maybe it was the carbon dioxide first, but it's not conclusive at the present time. But we do know that carbon dioxide and temperature rise up and down like two roller coasters, but precisely which led the other is not exactly known. Okay, let's move on now to the next listener phone call.
My name is Timothy, and I'm listening on WHCU live streaming. And where does coldness come from? The North Pole and the South Pole are cold. Does that come from outer space, the coldness? Thank you.
I think what you're asking is, where is the coldness of the North Pole and the South Pole come from? Well, it comes from the fact, not from outer space, but it comes from the fact that the axis of the Earth tilts. And when the axis of the Earth tilts toward the sun, then the northern hemisphere gets summertime. When the North Polar region points away from the sun, you get wintertime. And that is the origin of the seasons as the Earth goes around the sun. Now, why is it cold? Well, precisely for that reason. The equator is warm because on average, it gets the most amount of sunlight on average, where the North Pole and the South Pole on average get the least amount of sunlight. And so that's what drives the weather. What drives the weather is two things. First, sunlight and the fact that the Earth is tilted. And second of all, the rotation of the Earth, which gives us the winds like the jet stream and stuff like that. So the weather on the Earth is determined by basically two main factors, the sun and the rotation of the Earth as it goes around the sun. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And give us a call if you want to get on Science Fantastic. The number to call is 612-564-8135. All we ask is that you leave your name, call letters of the radio station if you're listening to one, and the city you're calling from, and then ask that question. Make that comment, and perhaps you can get on Science Fantastic with Professor Michio Kaku. Now, sometimes people email me and say, well, I'm too bashful to have my name heard on national radio, but you can send me an email. Go to the web and go to my website, mkaku.org, mkaku.org, and you can ask that question, and then perhaps I'll read your response on national radio. And go to my website, mkaku.org, mkaku.org is the website. If you go to my Facebook site at Michio Kaku, we have 3 million fans on Facebook, over 600,000 fans on Twitter. So find out what all the excitement is about. And let's say it's 4 o'clock in the morning, and you're all alone, and something just pops into your mind. Something about health, something about the future, something about evolution, something about DNA, something about the universe, but there's no one to talk to. Well, you can talk to me. You can give me a call. 612-564-8135 is the number to call, and then you can ask that question, make that comment, and perhaps you can get on national radio. And also, I've written 4 New York Times bestsellers. My latest one is called The Future of Humanity, about the future of the space program. We're talking about going back to the moon. Starting next year, an unmanned probe will be sent back to the moon. Then 3 years after that, we're going back to the moon with astronauts. Then on to Mars and beyond, perhaps to the asteroid belt, and maybe one day to the stars. Find out about what all the excitement is about by getting a copy of my latest book, The Future of Humanity, talking about the future of the space program. Okay, well, let's get right to the listener phone calls. So let's have the first call.
Hi, this is Tom Myers from Rochester, New York. I saw this on a tweet. What will it take to get the U.S. to use the metric system, period? Our students are being forced to learn 2 systems. Their main system, it gives them a handicap when they're using science. This is not a good thing. Thank you.
Yes, I sympathize with you wholeheartedly. When I go traveling around the world, I realize that everybody uses the metric system. Everybody talks in terms of meters and centimeters, except when they come back to the United States, it's back to the old U.S. system. Now, at one point, there was a national campaign years ago to convert to the metric system. However, it never materialized because of, well, force of habit. It costs money to make the change. And it also is a question of inertia, bureaucratic inertia. You see, politicians don't get points. They don't get reelected by being the champion of the metric system, and people are naturally conservative. Now, in other countries, they have to convert because if you want to engage in commerce, international commerce, then you have to go to the metric system. However, the United States is the 800-pound gorilla. As a consequence, we wanted them to conform to us. Let them convert metric system and our system. Now, it turns out this has practical implications. Years ago, we sent a Mars probe into outer space, and there was a miscalibration because of the conversion from the English system to the metric system, and our space probe was lost as a consequence. So in other words, this has million-dollar consequences. It's not just a question of inconvenience. It's also a question of mistakes are made as a consequence. But politicians have to get behind it, and unfortunately, there's no brownie points that politicians get by pushing something that's unpopular in this country like the metric system. I sympathize with you, but ultimately, it's up to the politicians. Sorry about that. Okay, let's move on to the next listener phone call.
Stephen Winter calling from Clinton, Mississippi. Radio stations 103.9 WYAB. My question is concerning global warming. If I'm not mistaken, when I was in high school in the 70s, they were talking about us coming out of a mini ice age or something like that. They were expecting it to get warmer back then. I just wonder what's happened between then and now. Was that information off track, or we got folks wanting to blame everything on CO2 emissions, which I believe one volcano produces a huge amount. Anyway, that's my question. Just curious about that. Thank you.
Okay, well, you ask a question that's very relevant for today. First of all, there are two kinds of atmospheric disturbances. One is long-term and one is short-term. Now, ice ages come and go on a scale of tens of thousands of years. The last ice age ended 10,000 years ago, and that made possible the rise of civilization. Civilizations could not exist when most of North America was covered with a half a mile of ice. And so we were basically nomads going from one small hunting site to another, chasing after the deer and the buffalo, who also migrated. And it was a very hard life. Then 10,000 years ago, the ice melted, making possible civilization. But these are long-term cycles. In another 10,000 years, we will have another ice age. In other words, 10,000 years from now, don't be surprised if America is under a half a mile of ice. Now, the other question is about global warming. Now we're talking about things that change the weather, not on a scale of tens of thousands of years, forecasting another ice age in 10,000 years, but cycles which happen on a scale of decades to centuries, which are usually not natural. Natural cycles usually take thousands to hundreds of thousands of years, but here we're talking about a change that's taking place on a scale of decades. When you look at the last 100 years, for example, you realize that since the Industrial Revolution, temperatures have risen about a degree, that also sea levels have risen at a very measurable rate, caused by the warming of the oceans. Now, the Earth is warming up. You can talk to any farmer, Any farmer will tell you that his or her livelihood depends on knowing when to plant and what the seasons are. And yes, summertime is about a week longer than before. So global warming, just in the sense of warming, is here. Even President George W. Bush years ago said, quote, something is happening, unquote, with the weather that even the average person knows. Now, here's where the debate comes in. The debate comes in as to how much human activity is responsible for global warming. So in other words, even the so-called skeptics will concede now the fact that the Earth is warming up. We can see this with satellite data, oceanic data, but then the question is, who's responsible? Well, we'll talk about that after the break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. Give us a call at 612-564-8135. You'll hear the beep. Leave your name, call letters of the radio station, and the city you're calling from, and then ask that question. Make that comment, and perhaps your thoughts will be heard on national radio. Well, before the break, we had a question about global warming. Yes, even the skeptics will say that the Earth is warming. And years ago, I was a skeptic myself. I used to say to myself, come on, now, give me a break. The Earth is so big, it's huge, and humans, we're so tiny. How can we humans influence something as big as the weather? But then you take a look at what's happening with the Earth itself. All the indicators show that the Earth is warming and it's accelerating. We see that all the major glaciers are receding. All the major glaciers are receding on the planet Earth. Parts of Antarctica are beginning to break off. The stability of Antarctica is now being questioned. We see the fact that summer times are about a week longer than normal. And we see that global swings of the weather are commonplace now. 100-year floods, 100-year forest fires, 100-year this, 100-year that. They seem to be happening all the time. And then the big question is, how much of it is due to human activity? Well, scientists use computer programs. Some people don't like them, but what else are you going to do? Use pencil and paper? When you use computer programs to run the videotape, what you find is that with 90% confidence, it is human activity. Now, 90% confidence is not 100%. Scientists are not saying that with 100% accuracy we say that it's human activity, but with 90% confidence, they say it's human activity that is causing the Earth to heat up. Okay, well, let's move on now to the next listener phone call.
Hi, Dr. Kaku. This is Ben in Chicago. Are atomic events recorded in space-time similar to the way in which digital data is recorded on storage media? And if so, would it be theoretically possible to read historical events of the past and then recreate them in the present? In other words, you'd be time traveling to the past, not to alter the past, but to gather data of past events and then recreate them in the present, so you could perhaps alter past events in the present. Doing this would avoid any time-traveling paradoxes, and it could be a way to resurrect a dead person by recreating their bodies and memories in the present time in a way that wasn't possible in the past. Thanks.
Well, you actually ask a question that I used to ask myself as a youth a long time ago. Let's say there's a crime. The light emitted from the crime has bounced off the walls, but if you could reassemble all the light, then you could in principle recreate the scene of the crime. So I thought to myself, wow, I mean, we have all this knowledge about atomic physics. We have all this knowledge about atoms and photons and electrons. Why can't we collect all this data, not digital data, but atomic data, and then run the videotape backwards to reconstruct the crime? Well, great idea, but in practice, it's not practical for several reasons. First of all, when light scatters off a substance, let's say there is a crime and light from the crime hits the walls, light scatters in all these different directions, and to recreate that wavefront would require you to know everything there is about the original wave, everything about the texture of the wall that bounced the light off, and the amount of data would be incredible. And so it's not possible using ordinary techniques to then recreate the wavefront. Sorry about that. However, some people have suggested that even though we can't duplicate the atomic data, the digital data may somehow be reconstructed to create an approximation of reality. This is called digital immortality. One Silicon Valley company is already offering to digitize everything known about you. Your credit card records, your Instagram pictures, everything known about you on the web can be digitized to get you a first approximation to who you are. Now, as time goes by, more and more information will be collected about you to the point that we may be able to reconstruct a reasonable facsimile of who you are. And the Silicon Valley company actually is offering to create a robot that looks like you, talks like you, has the same mannerisms as you. I've actually seen the robot, and it's not very advanced, so don't get your hopes up. But the question of digital immortality is a possibility. For example, take a look at Winston Churchill. Let's say you digitize everything known about Winston Churchill. So when you go to the library, you talk to him. You talk to a holographic image that reproduces the sound, inflection, historical notes, everything known about Winston Churchill. I mean, I wouldn't mind talking to Einstein. I'd have a great time talking to Einstein, or even a reasonable facsimile of Einstein. And then, maybe decades from now, the Connectome Project will be finished. The Connectome Project will map the entire brain. Every neuron of the brain can be mapped to recreate a facsimile of your thinking brain, including your memories, your personality. We're talking about a digital version of you that is immortal. Now, is it really immortal? Well, to paraphrase former President Bill Clinton, it all depends on how you define you. If you are a biological being, then no, this is nothing but a digital tape recorder. However, if you is the sum total of all the information that is known about you, your mannerisms, your feelings, your memories, everything known about you, if that is you, then in some sense we have digitized your soul. So your soul is now being reduced to information. Now, is this possible? Certainly possible. Is it economical and practical? That I don't know. But as computer prices continue to drop, some people may want the option of not biological immortality, but digital immortality. Okay, let's move on to the next listener phone call.
Barton Salen, listening on WSRQ in Sarasota, Florida. Since general relativity says that a clock on the sun would run slower than a clock on the Earth because of the greater gravitational force on the sun, if a clock could survive on the sun, doesn't that mean that those time differences between the sun's clock and our clock would accumulate, so that when we look at the sun today, we would not be seeing it as it is today, but rather as it was in the time of the dinosaurs? Now, I realize that today we see the sun as it is today because when there is a flare on the sun, if it's in the right position, we get hit a few hours later by particles from that flare. So we know that we're watching the sun as it is today. Thank you.
Yes, well, you ask a very interesting question. It turns out that the speed of gravity is the speed of light. If the sun were to disappear right now, it would take 8 minutes. 8 minutes for that information to hit the Earth. So even gravity has a finite speed. Now, as you pointed out, time beats at different rates throughout the universe. On the moon, time beats faster. So if I have a clock on the moon and a clock on the Earth, and the two clocks can talk to each other, the clock on the moon beats faster than a clock on the planet Earth. And this is actually measurable. So this is not science fiction. This is science fact. Get used to it. In fact, Einstein once said that he put a clock every at every point in the entire universe. You put a clock, all of them beating at a different rate, but he was so poor he couldn't afford a clock of his own. But it's true. Time beats at different rates throughout the universe. So you're saying, can you accumulate this difference in time? The answer is yes, but it is infinitesimal. So if I have an astronaut on the moon and an astronaut on the Earth, a twin, and they eventually meet years later, they will only be a fraction of a second delayed between the two twins. It's a very tiny effect. So don't think that it has any practical applications at all. But you're right, time beats at different rates. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open, that's right. It is open mic on Science Fantastic. Here's your chance to ask that question that you've always wanted to ask but never had the opportunity. You can give us a call at 612-564-8135. Leave your name, call letter to the radio station you're listening to and the city you're calling from, and then ask that question. Make that comment that you've always wanted to do. And remember, no question is too dumb to put on national radio. Sometimes the dumbest questions are the deepest and most profound questions of all. And also, go to my website, mkaku.org is the website to go to, mkaku.org. And find out about my 4 New York Times bestsellers about the future of science, the future of jobs, the future of economy, the future of space travel, all of it contained in my books. Okay, let's move on now to the next listener phone call.
Hey, this is Armand from Queens, New York. I listen to you on YouTube. I was wondering, why do you think Elon Musk thinks that we live in like a simulation, like we're a simulation pretty much. We're, made by computers or whatever. I know you believe in the multiverse theory. Well, why do you think Elon Musk believes that we're like a simulation or like a program? Thank you. I love your show. Have a great one.
Excellent question. Well, as I mentioned in my book, The Future of Humanity, we have Silicon Valley billionaires affecting the direction of the space program. And so these people made their money on the internet. For example, Elon Musk was a PhD candidate in physics, like Wernher von Braun, the famous rocket scientist. Elon Musk also went into the PhD program in physics, but after just 2 weeks at Stanford University, he decided, nope, this is not for me. The money is in Silicon Valley. So people in Silicon Valley think you can digitize everything. But you see, there are limits to what you can digitize. For example, how many atoms are there in your body? I mean, there are 10 to the 23 atoms in a mole. Your body consists of many, many moles. And so the number of atoms in your body could be on the order of 10 to the 26 atoms. That's an enormous number of atoms that you cannot digitize. Take a look at the weather. The smallest object that can simulate the weather is not a supercomputer. Even a supercomputer cannot model the weather and every atom of the weather accurately. The smallest object that can model and reproduce the weather is the weather itself. So we say that these things are not calculable. There are simply so many ways in which atoms can vibrate inside a gas to create the weather that it's simply not practical to build a machine that can duplicate every single atom bouncing around inside the atmosphere. Now, people and reality is much more complicated than the weather. And so that's why even classical physics, Newtonian physics, cannot be modeled using a computer. It cannot be digitized. Now, quantum mechanics makes it worse. Quantum mechanics says that all possible universes are possible, and so you would have to digitize not just one universe, you would have to digitize all possible universes in the world of quantum mechanics. And that's why I say that the movie The Matrix was great, but it's a movie. Get over it. It's a movie. We are not living in a simulation. When you hear the beep, leave your name, Call letter to the radio station and the city you're calling from, and then make that question. Make that comment about science, and perhaps your thoughts will be heard on national radio. Okay, let's move on now to the next listener phone call.
Hello, sir. My name is Dale Phillips. I'm actually not listening to a radio station. I'm looking you up online, and I'm calling from Bahrain, in the Middle East. My question is sort of have a two-part question. How close are we to making colonies on other planets, or even the moon, or making colonies elsewhere other than Earth, is what I'm trying to say. Exactly how close we are to doing that. And also, one of my favorite episodes of yours is the episode of Sci-Fi Science where you make the lightsaber. How close are we to making the lightsaber from the time you made that episode to now? So I apologize for the two-part question, but that is my two most favorite interests. So thank you very much. My name is Dale Phillips from Bahrain, and hope to hear from you soon. Thank you.
Wow, what a phone call. Yes, I've been to the Middle East, and yes, I'll try to answer your questions. First of all, the colonization of planets is still going to be decades away. Just last December, President Donald Trump issued the Space Policy Directive number 1. And that Space Policy Directive reversed the policies of Barack Obama. Barack Obama basically ended the U.S. manned space program. He canceled the space shuttle, canceled the replacement for the space shuttle, canceled the moon program, and then also canceled the Mars program. However, Space Directive number 1 says we are going back to the moon, then to Mars, and then beyond, perhaps the asteroid belt. Now, let's be real about this. The timetable, of course, is still speculative. Starting December of 2019, the end of next year, NASA intends to send the SLS booster rocket into outer space, and the capsule will go around the moon, unmanned capsule. Then, around 3 years after that, astronauts will go back to the moon. And then around 2030 to 2035, that's when the first astronauts will go to Mars. And then once we're on Mars, we have to set up a Mars colony. And that'll, of course, take even more time. Perhaps we'll use a lava tube as a makeshift base of operations to protect us against cosmic rays and the harsh atmospheric conditions of Mars. Then we'll create a power plant by putting out solar panels and then begin mining operations. Why that? Because ice is a valuable commodity. Mars has plenty of ice. It's a frozen desert. Ice can be melted and purified to give drinking water, broken apart into oxygen and hydrogen to create rocket fuel for the return mission. So again, first we go to Mars, put our flag on Mars, set up a impromptu base of operations, but then we're talking about long-term operations, basically starting mining to extract water. After that, we're going to set up a agribusiness. In other words, we're going to use genetic engineering to create varieties of algae and crops that can be sustained in the harsh conditions of Mars. The goal is to make it self-sustaining, so it's not going to cost anything at all. For example, it turns out that Mars rock can be melted using microwave radiation. This has actually been done in the laboratory to create duplicate rock of Mars, hit it with ultraviolet radiation, and melt it to create brick. So in other words, it's possible to use the soil of Mars to create brick, which will be used as building materials. It'll be possible to mine the ice to create the first mining operations, and then melting the ice caps using solar satellites to beam the energy down to the poles. Now, we're talking decades. We're not talking anytime soon. But you got to start somewhere. And maybe mining the asteroids could help pay the bill, because the asteroids have plenty of platinum chemicals. Well, unfortunately, that's it for Science Fantastic. Once again, if you want to get on Science Fantastic, give us a call at 612-564-8135 and ask that question. Make that comment that you've always wanted to do on national radio. So this is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science and technology that touches your lives and changes the destiny of nations. And again, if you want to get on Science Fantastic, give us a call. The hotline number is 612-564-8135. And again, leave your name, call later to the radio station and the city you're calling from, and then ask that question. Make that comment that's always been bothering you about science. And once again, no question is too dumb to put on national radio. Years ago, a 16-year-old boy asked a really dumb question. Can you outrace a light beam? It took him 10 years to answer that question, from the age of 16 to the age of 26. But when he was 26 years old, he finally answered that question. Can you outrace a light beam? Well, that 16-year-old boy was called Albert Einstein, and his theory changed the destiny of humanity. He understood what makes the stars shine, the energy behind atomic and hydrogen bombs, the technology that we see in our living rooms in the form of the internet, transistors. A lot of this technology goes right back to Albert Einstein, who asked himself a simple question: can you outrace a light beam? So you can also be part of the March of Science by giving us a call at 612-564-8135 and ask that question. Make that comment. Well, before the break, we had a two-part question, and that is, what would it take for us to build a colony on other planets? And, well, in the 2030s, that's the earliest we could have humans on the red planet. And then it'll take decades after that before we set up the first mining operations. We set up the first agribusiness, and we make it self-sustaining for colonists. And then to create a paradise on Mars, we would have to send solar satellites to then beam solar energy down to the polar ice caps to melt the polar ice caps so that liquid water flows on the surface of Mars once again. And so hopefully, perhaps late in this century, we will have a self-sustaining Martian colony that's not going to cost anything, so that colonists will have a self-sustaining economy based on mining operations, based on agribusiness, to create a permanent settlement on Mars. And then beyond that, well, get a copy of my book, The Future of Humanity, where I talk about going beyond that to Europa, to Titan, and then perhaps even to the nearby planets surrounding other star systems. Now, the other part to the question that we had earlier was the lightsaber. Well, for the Science Channel, I once hosted a science series where we went through the hardware of science fiction, looking at them from the point of view of a physicist. So we looked at the lightsaber. Now, first of all, the lightsaber has a problem, and that is it extends a finite distance from the hilt. Now, how do you do that? Light, of course, simply keeps on going forever unless it bounces off something. So one way in which you can create the temperatures of a lightsaber is with a plasma torch. Plasma torches are actually commercially available. It's basically a large spark that can create a plasma. Now, a plasma is the fourth state of matter. We have solid, liquid, gases, but the sun is not made of a solid, liquid, or gas. The sun is made out of a plasma. That is a gas of dissociated atoms, atoms that have been broken up, and you can create plasma using electricity. So if I have a plasma torch, then I could use that to cut right through steel, for example, and simulate a lightsaber. However, it's not a true lightsaber in the sense that it goes a finite distance. A lightsaber, of course, is based on light, which can in fact go an infinite distance. But this is as close as you can get to a lightsaber using today's technology. So the lightsaber would have to have a spine. It would have to have a spine that then emits the plasma from the spine and then creates the lightsaber. Now, it is not exactly what you find in Star Wars, but it's as close as you can get using today's and tomorrow's technology. Okay, let's move on to the next listener phone call.
Yes, Dr. Kaku, this is Justin from Texas. I listen to KMET. I was just wondering, what do you think the current administration of the United States is going to do about the problems we have with the space station, International Space Station? What do you think? They're talking about, I guess, renting it out. What do you think the best idea would be to use with the International Space Station? Thank you very much.
Well, you ask a very embarrassing question because at the present time, we don't know what to do with the International Space Station. First of all, let me explain what the administration is doing. The Trump administration has issued, at the present time, 3 space directives. Space Policy Directive 1 talked about going back to the moon, then to Mars and beyond. The second directive talked about private enterprise and encouraging the deregulation of outer space. The Space Directive number 3 talked about space junk. So the administration has not yet stated what its policy is toward the space station. Now, it depends on who you talk to. If you talk to a pure scientist, they would say that we get actually very little new science from the space station. So they say that we perhaps don't even need a space station. Other people say, what a waste, $100 billion, and we're just going to let it deorbit and burn up like a meteor. At the present time, the only practical application would be to commercialize it. But we'll see. But unfortunately, we have run out of time in Science Fantastic. Once again, you are listening to Science Fantastic with Professor Michio Kaku. Join us every week when we discuss the cutting edge of science, and go to my website, mkaku.org, mkaku.org, and find out what all the excitement is about.